Lagrange's partial differential equation, every time comparing ratios of the auxiliary equation might not be helpful to arrive at the solution. So we may also depend on method of multipliers to arrive at the solution. When we have ratios a1 by b1 equals a2 by b2 equals a3 by b3 equals k, when we choose numbers lmn such that la1 plus ma2 plus na3 upon lb1 plus mb2 plus mb3 is considered, this ratio also maintains the same proportionality maintained by these three ratios individually. So this concept is used to solve Lagrange's partial differential equation. When we wish to find out solutions for Lagrange's partial differential equation of the form u equals c1 and v equals c2, we may choose either numbers lmn or functions of x, y, z to multiply along with the numerators and denominators and add up the numerators and denominators correspondingly. And these multiplication is done on the ratios of the auxiliary equation such that LP plus MQ plus NR considered either becomes 0 or is proportional to either of the functions P, Q or R, or a combination of these three functions P, Q or R. Let's look at example. Solve y square plus z square into p equals xyq minus xz. We identify that this is of the format Lagrange's partial differential equation. This can be written in the format pp plus qq equals r. So we bring this xyq to the LHS so that it becomes pp plus qq format, and minus xz is written in the RHS itself. So we could identify the functions p, q and r. P is y square plus z square, q is minus xy, and r is function minus xz. So we write the auxiliary equation or the subsidiary equation for the given partial differential equation: dx by p equals dy by q equals dz by r. When we compare the last two ratios, we can cancel x minus x, which is common to both the denominators of dy and dz. After cancellation, we are left out with dy by y equals dz by z. When we integrate both sides, we obtain log y equals log z plus log a, where log a is the constant of integration. This can be written as log y equals log a z because we have log a plus log b equals log ab. Now when we bring log a z to LHS, we have log y minus log za equals 0. We have log a minus log b equals log a by b. Therefore log y minus log za equals log y by za, and the RHS is 0 itself. When you take exponential function on both sides, that is e raised to log y by za equals e raised to 0 is considered, we have, since exponential function and logarithmic function are inverse functions, e raised to log y by za becomes y by za itself, and e raised to 0 equals 1. Thus this equation, when raised as the power of exponential function, it becomes y by za equals 1. When you bring the constant a to the RHS, we have the equation of the format u equals a, which is the expected solution. So the first solution for the Lagrange's partial differential equation is y by z equals a. Notice that even if we compare any other ratios of the auxiliary equation, it's not very easy to attain the next solution. So we will depend on method of multipliers. If we choose multipliers L, M, N such that L equals X, M equals Y and N equals Z, and when we consider LP plus MQ plus NR, we have P equals Y square, Q equals y square plus z square, q equals minus xy, and r equals minus xz. Therefore, LP plus MQ plus NR, where L equals x, M equals y and N equals z is obtained as xy square plus xz square minus xy square minus xz square equals 0. Here we selected L, M, N as functions of x, y, z, and when we evaluated LP plus MQ plus NR, we obtained this expression as 0. Here we observed that when we took LDX plus MDY plus NDZ and the corresponding multiplication and adding LP plus MQ plus NR in the denominator also, which when equated to a proportionality constant k, since the denominator vanishes, we have the denominator when multiplied to k also get vanished. Therefore we have L dx plus M dy plus N dz equals 0. Here we have L equals x, M equals y, and N equals z. Therefore L dx plus M dy plus N dz equals 0 can be written as x dx plus y dy plus z dz equals 0. Here we selected LMN such that the denominator entirely vanishes. Whenever you have such a combination, you can easily equate the combination L dx plus M dy plus N dz equals 0 because of this reason. This combination when get multiplied with the proportionality constant and ultimately attains 0 value, you can equate the numerator to 0. Now when you directly integrate, here integration done with respect to x, integration done with respect to y, integration done with respect to z, we have x square plus y square plus z square equals a constant of integration. Since during integration, each term is having 2 as the common denominator, which when taken to RHS becomes another constant b. So now we have obtained the second solution of the format v equals b. Since we have obtained two solutions u and v, we can write the general solution phi of uv equals 0 or u equals phi of v.